When we measure heat, we measure it in units of calories or joules. Now, if you're thinking calories like food calories, you're absolutely right. But if you look here, it's a lowercase c calories, whereas a food calorie is actually a capital C calorie. And so 1,000 lowercase c calories is equal to 1 food calorie. So you can think of a food calorie as a kilocalorie. 1,000 calories is equal to 1 food calorie. Joules, sometimes you'll see it as kilojoules, so same thing. 1,000 joules is equal to 1 kilojoule. So when there is a temperature change, heat can be calculated using the formula Q equals mcΔT. So Q, if you forgot, represents the heat that's absorbed or released. M is mass, so we have the units grams. C is specific heat capacity. And delta T, triangle T, is a change in temperature, final temperature, minus the initial temperature. When the temperature does not change, so we're talking about a phase change during the plateaus of our heating curve, we're going to use the values of molar heat of fusion or the molar heat of vaporization. So let's jump into our first example. So the first thing here I want to point out is that I gave you tables of specific heat capacities of 4 different metals, and over here on the left we have the molar heat of vaporization and the molar heat of fusion of water, ethanol, and methanol. So you need to figure out which value we're going to use for all of the problems that we're going to look at today. So the first problem says, how much heat is absorbed when 42.0 grams of gold goes from 25 degrees Celsius to 35 degrees Celsius? The first thing you need to ask yourself is there a temperature change? In this case, yes, there is. It's going from 25 degrees to 35 degrees Celsius. The reason why that question is important is because it will tell you which method to use. Will you be using Q equals mcΔT, or will you need to use heat of vaporization or fusion? And in this case, we'll be using Q equals mcΔT. So the next thing is we want to figure out which of these specific heat values we're going to use, right? So this substance is gold. So we want to go ahead and find gold on our table, and there it is. Okay, so we'll be using 129 joules per kilogram degree Celsius. So let's go ahead and plug it in. Mass is 42.0 grams. Specific heat is 129 joules per kilogram degree Celsius. And the change in temperature, remember it's final minus initial, so it's 35 degrees minus 25 degrees Celsius. You want to pay close attention to the units. You want to make sure that all the units are going to cancel each other out. And if you look at this here, this right now cannot cancel out. We have grams and kilograms. So then what are we going to do? We're going to go ahead and convert, right? So we will convert 42 grams to kilograms because that's the easiest thing to do. So 42 grams, bring down grams, and kilograms will go on top. 1,000 grams is equal to 1 kilogram. So we're dealing with 0.0420 kilograms. So let's rewrite that with our new mass. We're going to go ahead and calculate the temperature change, which is 10 degrees, and go ahead and cancel out the like units, kilograms and Celsius. Multiply, and we get 54.2 joules of energy. Example number 2. How much energy is given off when 3.2 moles of steam condenses to liquid water at 100 degrees Celsius? Again, the question is there a temperature change? No, there isn't. The temperature stays at 100 degrees. In fact, it's telling you that steam condenses to liquid. These are key things from this problem. Why? If we look at the heating curve, we're looking at which section? We're looking at DE, right? And so what does that tell us? That tells us that we'll be looking at the molar heat of vaporization. And we're looking at the molar heat of vaporization of water, so we're looking at 40.7 kilojoules per mole. Now how do we set this up? Well, we're going to start with what we're given, 3.2 moles of water. Now, 3.2 moles of water, we're going to use the fence, okay? We're going to bring down, the method is exactly the same, we're going to bring down moles, but what do you think is going to go on top? Well, if you take a look at the screen, there's only one thing that can go on top, and I'm not talking about grams, I'm talking about up here, it says kilojoules per mole, so we're going to write kilojoules on top. So remember what those units actually represent? It means, for example, with the 40.7, it means 40.7 kilojoules per 1 mole. So like units will cancel out. We're going to multiply and divide, and we get 130.240 kilojoules. Now that is not considering significant digits, so our final answer is 130 kilojoules. Example number 3. Calculate the heat required to melt 125 grams of ice at its melting point. So again, is there a temperature change? No. Temperature isn't mentioned at all. But we do know that it's ice, and we do know water's melting point, or we should, which is 0 degrees Celsius. And so what is this telling us? That we are looking at section BC of the heating curve, so we'll be looking at the molar heat of fusion. Okay, so let's start off with what we're given, 125 grams. But you'll notice that we can't bring down moles, right? We're going through the same method for the fence that I taught you, and we're going to bring down grams. Well, from here, where can we go? Well, we want to convert grams of water to moles of water, right? So we're going to put moles of water on top. This is the molar mass of water, and by now, hopefully you know what that is. It's 18.02 grams of water is equal to 1 mole. So grams will cancel out. Now we're going to bring down moles, and up top we're going to put kilojoules. 6.01 kilojoules is equal to 1 mole. Multiply and divide, and we get 41.7 kilojoules of energy. And that is with the correct number of significant digits. Okay? Example number 4. What mass of copper in kilograms at 150 degrees must be added to 7.0 kilograms of water? Specific heat is given. That is initially at 15 degrees Celsius if both materials end up at 30 degrees. Whoa, right? This is different from examples 1 through 3. How is this example any different? Because this example has 2 substances, right? We have copper and we have water. Okay, so what are we going to do? What is our method? Well, we're going to actually look at the law of conservation of energy that states quantity of heat lost by the system is equal to the quantity of heat gained by the surroundings. So mathematically, what does that mean? Negative Q is equal to positive Q. The energy that's released is equal to the energy that's absorbed. So negative MCAT is equal to positive MCAT. Okay? So let's start there. We're going to go ahead and designate one side copper and the other side water. And let's look at what's going on. We're trying to find the mass of copper, so that'll be X. C is up here, copper, right? Specific heat of copper, 387 joules per kilogram degrees Celsius. And it is initially at 150 degrees. What's the final temperature? The final temperature is 30 degrees. Okay, so we want to do 30 minus 150. And now let's look at the other side. We have 7.0 kilograms of water. Specific heat is 4.18 joules per gram degree Celsius. It's initially at 15 degrees. It ends up at 30 degrees, so 30 minus 15. Okay? Now, before we even try to solve, let's make sure our units will cancel out. On the left side, for now, it'll cancel out. On the right side, will it cancel out? No. If you look here, there's kilograms and grams. So we want to go ahead and convert the kilograms before we try to solve this problem. So 7 kilograms, 1 kilogram is equal to 1,000 grams. So we're dealing with 7,000 grams. So let's go ahead and rewrite that number. Instead of 7.0 kilograms, we want to write 7,000 grams. So now take a look again. Will our units cancel out? Yep, grams cancels out. Degrees Celsius will cancel out. So let's go ahead and do our next step. And then we're going to solve for X here. Our units, will it cancel out? Yes, it will. Joules cancel out when we divide. And so we have a mass of 9.5 kilograms of copper. Okay, so the common mistake here is that most students will mix up the temperatures. Okay, so a lot of them will put like 30 minus 15 for copper, and then 30 minus 150 for water. So you just have to make sure that you're double checking your temperatures, okay, and making sure that they're on the right side, that everything that's of copper is on the copper side and everything that's of water is on the water side. All right, example 5. A hot piece of silver at 65 degrees Celsius was dropped on a 25-gram ice cube at 0 degrees. After a few minutes, both the silver and the water stayed at 0 degrees, but the ice melted completely. Explain why the heat from the iron did not raise the temperature above 0 degrees. So I want you to think about what is going on. Why did the temperature not go up? Why, if you're thinking about the heating curve, why is it staying at 0 degrees Celsius? What is going on there? Remember, we talked about the potential energy. What is the potential energy doing? It's increasing. And so what is happening at a molecular level? Molecules are rearranging, molecules getting further apart, and ultimately intermolecular forces are breaking, right? So that's what's going on. And that's the reason why, even though the substance is absorbing heat, it's not changing temperatures just yet, okay? All right, next part. What is the mass of the piece of iron? Well, this example is similar to our previous example, right? We have two different substances, silver and water. So we're going to do negative Q equals positive Q. We're going to designate one side as silver and the other side as water. And if you're wondering, does it matter which side is which? No, you'll get the same answer no matter what, even if water was on the left and silver was on the right, okay? Again, the most important part is that you are keeping the numbers for silver on the silver side and the numbers for water on the water side. All right. So the next question is, are both of these substances going through a temperature change? Well, silver, it says, is going from 65 degrees to 0 degrees. So yes, that one is going through a temperature change. How about water? Water is not, right? It's saying that water stayed at 0 degrees and that the ice is melting completely. So are we going to set it up like MCAT? No, we're not, right? We're not going to set it up like MCAT. This is going to be similar to examples 2 and 3. Instead, we will be using the molar heat of fusion, okay, because there is no temperature change. So let's see what this looks like. So on the left side, we're solving for mass of water. We have specific heat capacity of silver as 235 joules per kilogram degree Celsius. And then the temperature is final 0 degrees minus initial 65 degrees Celsius. For water, we're going to go ahead and set up the fence. We're going to start with 25 grams of water, okay? And then we're going to convert that to moles, 18.02 grams per mole. And we're going to bring down mole and use the heat of fusion, 6.01 kilojoules per mole, and we get a total of 8.3 kilojoules. Now, if you take a look here, before we even solve for x, will our units cancel out? So if you take a look, here we have joules, and this is kilojoules. When we try to solve for x and divide, our kilojoules and joules will not cancel out, right? So what do we want to do to this number? Well, we want to go ahead and convert it to joules, right? We want to go ahead and convert the number that has the lone unit, not one that has 2 units like this, okay? So 8.3 kilojoules is going to equal how many joules? It'll equal 8,300 joules. We're going to go ahead and solve for x, and we have a mass of 0.54 kilograms of silver. And that's it for thermochemistry.